Recording.
This conference will now be recorded.
Hi, everyone. Thank you for joining our 25th meeting for the Time Appliances project. And it's a very nice milestone to have, 25. So a couple of updates before I'll introduce today's guest. First is that we are at the last stretch of contributing our very first specification. It's a reference architecture for the open time server. So for the guys who are new to this reference architecture, I put the link in the chat box, and you have the ability to review the different contributions there, whether it's on the software or on the hardware side. And we are welcoming everybody's feedback. This will be a good time for you to share with your colleagues and people of interest to see if they would like to contribute from their experience or ask any questions around it. Oleg from our team is leading this effort and will be standing by with any of your feedback. This will be the first contribution, and there are furthermore contributions from the other work streams we're working on as described on the wiki page. I won't go into all the rest, but for now, the open time server is where we put the focus, and we're asking for your collaboration. So thanks in advance. Another good update is that in November, we will have the Open Compute conference. It's going to be hybrid mode, and us, the TAP team, we do plan to have demos and presentations happening in that event. As for the details, probably they will come in the next meeting or so once we figure them out. And if there is anyone here who would like to help us with either demonstrating our technology that we are promoting, or by presenting in any of your possible contributions or papers, please reach out to either Ahmed or myself, and we will definitely be very happy with your support. So that's going to happen in the month of November this year. I think this would be all for the updates section today, and I'll turn now into today's guest speaker. We are hosting both Charlie and Benoit, who will be talking today about implementation of GNSS time receivers and how to overcome some of the problems that we are all facing in our deployments with disturbances, whether they are jamming or spoofing, and some other challenges when it comes to practical usages of GNSS. Charlie, I will be reading now his short bio. Charlie is an industry professional with comprehensive experience in RF engineering, sales of components and system channel management, developing new markets and products. And Benoit serves as head of field application engineering at Furuno and is responsible for providing in-depth technical support to Furuno's customers in Europe during pre-sales, product development, and post-sales. I hope I gave a good enough introduction to you too, and please feel free to complement any other useful information I forgot. So over to you, Benoit and Charlie.
Thanks very much.
Thank you, Elad. Well, first, maybe let me start by thanking Ahmed for inviting us to present at this meeting. And Elad, thank you very much for this introduction. And thank you to everyone for attending. And we can do it in a way that it is interactive. And if you guys have any question, you can interrupt me and we can discuss it right away instead of waiting to the end. I mean, except if there is a rule that is the other way around.
There are no rules. We definitely encourage interaction, conversation. There is a chat box. If you guys are too shy to use your microphone, you can always type it in and I'll try my best to raise the questions coming from the chat group.
Okay, so I'm just gonna introduce Furuno very quickly and our product so that everyone knows what kind of product we're talking about, and so where in which kind of product this technology is implemented. And just to make it clear, the technology we will be discussing, this is currently implementing in our product and not some kind of future plan that may or may not happen. So here we go. So, oops. So Furuno is a Japanese company based between Kobe and Osaka. And this company was started in 1948 to commercialize the first fish finder. And then from then on, Furuno involved in developing many other technology for the marine industry. So basically, pretty much any electronic component or electronic product for the marine industry, Furuno provide them. And throughout the years, they developed different kind of system, but in 1986, they developed the first GPS receiver for the boat application. And from then on, Furuno created different kind of product from this GPS receiver, not only navigation system for the boats, but also their own modules to start, and then later on their own chip. And today we make a chip and we make modules and we make finished product with these GNSS receivers. So here is what we have. Today we have a multi-GNSS receiver. This is called Opus 7. Actually, this comes from a company originally that was acquired by Furuno based in San Francisco, where I was at before. And with this chip, we make different kind of product. We make GPS receivers for the automotive industry and for the industrial application. But this is not the focus of today's talk. What we're going to discuss today is the timing and the frequency synchronization product that we make with this chip. So here are the different products that we make using this GNSS receiver. So we have a chip. We can also provide a timing chip or a timing modules. And then we make disciplined oscillators. So basically a GNSS receiver and an oscillator, usually at 10 megahertz. And then we make also finished product like this TB1 or this GF8646, which are more high-end finished goods, either with an OCXO or with a rubidium oscillator. And these are the different applications where those can be used, as many of you know, mostly in communications and networks, but also in labs and now also in some vehicle to road communication. So some of the market where we sell this product, so the mobile servers or the mobile base station and all the mobile networks, time servers, and then also broadcasting. And in Japan, we also use this product in seismometer to detect earthquake. Okay, so how do we characterize a GNSS receiver for timing application? Well, the position accuracy is important, but what is the most important is the time accuracy and the time stability. Many GNSS timing receiver manufacturer only spec one thing, and usually that is the stability, but called accuracy. We differentiate it and we specify both, and our receivers achieve 40 nanosecond accuracy, so basically in reference to UTC time, and a stability of 4.5 nanosecond at 1 sigma. So here is the list of all our different products, and all of them achieve at least 40 nanosecond accuracy, and the discipline oscillators have different kind of accuracy whenever the GNSS lock is lost, which usually doesn't happen, but can happen if there is an antenna failure, like a lighting strike on an antenna. Then it could be that the GNSS receiver has lost its antenna and is not able to lock to satellites. And so we're still able to provide an accurate time for, here we spec for 24 hours, but I would say most of this time we can still provide an accurate time up to 7 days with larger number than what is shown here, but not that much larger. And all this receiver, all our discipline oscillator, like you can see at the bottom here, they meet the PRTC-B requirement for time deviation and for MTI, so that's maximum time interval error. And our GT88, our timing receiver, also almost meets it, but not always for the small toe. But when integrating that kind of receiver in a finished product, you would have like a low pass filter on the output, and then this product will meet the PRTC-B. But all this is good, and I would say other manufacturers are able to achieve similar performance in open sky environment, and we do too in open sky, but we have spent a lot of time developing technology where we can achieve this performance also in challenging environment with AV multipass, and this is what I will be presenting a little bit later. This is like showing the holdover performance. So basically up to 0, you're locked to the GNSS signal, and when you're not locked anymore, then the oscillator is not free running, but it is disciplined based on what the GNSS receiver has learned from its behavior and basically applying it. So it's basically a PLL control based on how we have learned the behavior of the oscillator. And you can see that even temperature variations are not changing very much the behavior of the oscillator and the change of accuracy, and that's because we are using oven control oscillators. So small temperature variation have very limited effect. So here is the core of what we will be presenting today. So the mitigation effect for jamming, spoofing, and multipass, and non-line of sight satellites.
Perfect. These are all very relevant for our use cases, and I'm sure that the folks here on the call and the ones listening to us offline would find that interesting. Thanks.
Thank you. So what are the different kind of cause of degradation of the GNSS signal? Well, one could be the GNSS segment itself, so like the GNSS signal being wrong or being distorted, basically coming from the satellites. There is different things we can do, and we have different algorithms to mitigate that. So, for example, TRAIM and some other algorithm that control the data. The data we decode from the satellites, we verify them, and if we think that either the one from a satellite is not in line with the other, or one from a constellation differ from another, then we don't use the satellites that seems to be out of orders. But that's very rare. Other kind of disturbance are environmental disturbance. So multipass, lightning, ionospheric errors, those are fairly common. Another common one is jamming, whether intentional or not. And then rare but could be really disturbing is spoofing. And then the last one would be adjacent band transmitters. broadcasting, not really jamming signals, or I mean, not in the sense that it would jam the GNSS receiver, but more like the data would be decoded and somehow disturb the GNSS receiver. But this is under review. We've never seen it, although this has been mentioned as a potential way of disturbing GNSS receiver. So what do we have as solution against the common threat? So multipass, lightning, ionospheric errors, jamming, and spoofing. So for the one marked in gray, like ionospheric error and GNSS segment error, it's multiband and multi-constellation. Those are the two ways of eliminating these errors, on top of having special algorithm in your receiver to basically detect errors and eliminate the satellites. Against adjacent band transceiver, against lightning, and against jamming, we have implemented an active anti-jamming. We have implemented holdover in our disciplined oscillators, and then of course multi-bands help. And sometimes even multi-constellation can help, because, for example, so at L1 at 1575 megahertz, this is the L1 band for GPS. There you have GPS, Galileo, and Beidou now transmitting in that exact band. And then GLONASS is a few tens of megahertz away, around 1600 megahertz. Sometimes if the jammer is really centered at 1575 at GPS L1, it can be that if you still have a multi constellation receiver supporting even just GPS and GLONASS, that you can still get good time and good position, because, well, GPS can be spoofed, can be jammed, but GLONASS not. So that can also help. And then against spoofing, we have developed some anti-spoofing technology. And then against multipass, we have a new algorithm. It's a patented algorithm that we developed with NTT, and that's called dynamic satellite selection, and we're gonna discuss that. So anti-jamming function, what do we do then? So so we can differentiate two things. There is the jammers that are strong enough to basically disturb the reception and prevent the receiver from seeing or being able to track as many satellites as it's visible. But they could be also that the jammer is so strong that it saturates the whole RF path. Then in that case, well, unfortunately, there is not much we can do. But when it's strong, but not so strong, so basically the receiver can still receive the signals, but they are masked, then there is ways to overcome that. And one of them is to have like scanning the GNSS band and look for power in that band, and then apply notch filters anytime you find power at different frequencies. And that's what we have implemented in our current GNSS receiver, and that works quite well. So in this graph and in this test bench that we are showing here, we are testing it in that way, where we use a GNSS receiver to apply the signal to the receiver, and then with a RF coupler, we bring some jamming signals from a signal generator. And there we look how many satellites we are able to receive at the start of the test, where the jammer has a power of minus 100 dBm. And then every 30 minutes, we increase the power of the jammer by 10 dB. And you can see that the red curve, when AG, so anti-jam, is off, at about minus 70 dBm power for the jammer, you start losing a lot of satellites. So basically, we were tracking 25 satellites, and now we're only tracking like 6 or 7 satellites. So the receiver is still working, but it's being affected. when you turn on the anti-jamming, which by default is active, then the same thing happened, but it happens when the jammer signal power is at -40 dBm. So basically this is giving you 30 dBm or 30 dB of improvement in terms of jammer sustainability. So this is very useful either in an environment where you may have a lot of other electronic equipment transmitting and basically creating a lot of noise, so basically unintentional, but still a lot of noise. And sometimes it's not really easy to clean the environment and improve it and make it better. So the anti-jam will just bring that improvement. And then it can also help against malicious actors trying to jam a GNSS receiver. Anti-spoofing function. There, without entering into the details on how we detect spoofing, but basically we look at timing of signals and also the data that we decode from these satellites, if they match what we have seen before, and different kind of checks. And then from that, we can detect if there is a spoofing. And how were we able to verify that and make sure that this technology is efficient? So what we did there, we created with a GNSS simulator, we created a scenario that was well matching the live sky signal. Because if it's not really matching the live sky signal, most of the time the GNSS receiver will notice it and either discard just not use the spoofing signal, or just lock onto the spoofing signal, depending on if they are of a much stronger power or not. But if the spoofing signal match fairly well the live sky signal, then it's difficult for a receiver to even notice that spoofing is going on. And our goal here is to detect spoofing and to notify the user that there is spoofing. And then the ultimate goal is to overcome the spoofing. So basically not being fooled by it. But at the minimum, the goal is to report it so that the user can decide, or at least be warned, there is spoofing. I probably need to pay attention. Maybe I should switch to holdover, or maybe I trust more the time coming from the network. Basically, at least the information is known. And so we created a scenario that was very, very well matching live sky signal, but that contained some spoofing information. And we did a comparative test. So one receiver, the reference receiver, was receiving only the live sky signal versus the other one, the one which we wanted to test, was receiving both the live sky signal and the signals from the simulator, so the spoofing signal. And we compared their PPS, the stability of their PPS, and also if the receiver was able to notify that spoofing was happening. And you can see that the graph under here is showing that spoofing is being detected. And so unfortunately, it's not really easy to see because there is two curves on top of each other, but and the scale is not high enough because it was a test over many hours. But basically, the spoofing signal is being raised every time the simulator is transmitting, and so spoofing signals are there. So the first objective was to detect well-designed spoofing signal and report it. So this is working. And then what we did is we looked at the PPS, the stability of the PPS. And you can see the first graph here is showing in light gray whenever the spoofing is happening, and in red it's just the 1 PPS signal. And we can see that there is no significant jump or change of phase delay or of the PPS whenever spoofing is happening or when spoofing is turned off. So basically, spoofing is being detected, but it's not impacting the receiver. So it could be that our receiver was well designed, or it could be that our spoofing signal were not so hard to detect, that our receiver was not being tricked. So we took a different receiver from a different manufacturer, but a very recent one, so that we are sure that, you know, they have latest technology in the receiver, and we swapped the receiver and tested it. And there we can see that whenever spoofing was happening, this receiver was disturbed. So this is not to criticize anything or just to badmouth anyone, but it's just to prove that our technology is working.
So that was tested in a production environment or in a lab environment?
So this is tested in our lab because, well, it's forbidden to spoof GNSS, and so we can't really do it and broadcasting it. That's why we do it mostly with simulator. We have done a few tests also with antennas and in special labs, but the easiest was just to do it in a lab with a rooftop antenna and then the simulator simulating the spoofing signals.
Okay.
Yeah. And the reference receiver at this 10 megahertz output was to synchronize with the counter. So that way we know that the counter is also triggering well on the PPS and able to well compare the PPS from both receivers. So this was the anti-spoofing function. Now the multipass mitigation and the non-line of sight signal mitigation. So to be able to provide accurate time, a GNSS receiver basically needs to receive many or several satellites with line of sight view, so that there is no disturbance, so no attenuation, no reflection, no diffraction of the signal. And then in this case, most receivers most timing receivers are able to provide accurate time and stable time. But whenever diffraction in the signal happen, or reflection or attenuation, then it starts to be difficult for a timing receiver to continue output stable time. So we have recognized that problem for many years, and in this Opus 7 chip, we had implemented at start some kind of mitigation algorithm that worked very well against a multipass, where basically the reflected signal have a long travel time. So when the delay, when one satellite signal is received with large delay, then this was very efficient. But the problem is, when you use a GNSS receiver in an urban environment, you have signal with no delay, you have some with long delay, but we have often many with medium delay and or fast changing delays. And in this case, the technology we had implemented was not strong enough to overcome that. So we spent a lot of time reviewing what could we do there, and we worked with NTT from Japan, so that's the telecom carrier of Japan, and together we made first a lot of experiment, and then tried to implement a workable solution. So here is the test we did in NTT labs in Tokyo. So we placed the receiver in the courtyard, like at maybe a few, like 50 centimeter or a meter above the ground, and in this surrounded by these 3 buildings. Those buildings are not super high, but they were a good test case for NTT, representing where they have usually problem to place the GNSS antenna. And you can see that the view of the sky has some obstruction. There is some windows, so there is definitely a reflection, and there is also a portion of open sky. So here we're gonna receive signal with large and small delay and no delay. So a good mix of everything. And so it's gonna be difficult. So first, as I said, we did a lot of measurement and we tested our receiver and the one of our main competitors. And we tested it first in open sky, so on the top of the building. And there we can see that all these receivers achieved a time accuracy that was within the PRTC-A requirement, which is less than 100 nanoseconds. Our receiver was achieving 21, so that was clearly better, but okay, that's open sky. Then we moved to the courtyard where I showed just before, where we placed the antenna, and there we repeated the test. And yet ours is the first one on the left, had a better stability, but the accuracy was poor. So basically all receiver failed. No matter, maybe it's slightly better, it still failed. It doesn't meet the PRTC-A requirement. So we decided that here we really needed to do some work. And so we went back to the drawing board and we decided we need to find a way to work with signal where we are able to detect or to judge which ones are in line of sight, which one are attenuated, which one have delay that are large enough so that they should be rejected, and which one have very small delay that could be used in complement of the one that are in line of sight in case there is not enough line of sight satellites. Because if there is not enough line of sight satellite and you remove all the other one, you may have trouble getting a time anyway. Okay, that is a statement that is especially valid when at the start of a GNSS receiver, because most timing receiver, they will operate for many hours, like 24 hours or 48 hours to survey their position. And then once they have surveyed their position, they switch into time mode. And when they are in time mode, then most receivers can continue output valid time with only one satellite, with only tracking one satellite. But before that, when in the survey period, if they don't have enough satellites and these are not accurate enough, then the survey position will be wrong, and then the time will never be accurate and probably also not stable at all. So we did that. We decided, okay, we need to find some algorithm to find which satellites can be trusted, which one cannot be trusted. And then once we found some way to measure the different signal and establish a good way to detect which one are stable, which one have too much delay, which one not. Then we fine-tuned our algorithm.
Benoit, one quick question. So this algorithm, what would be the convergence time? I mean, I'm trying to think, does it run on hardware or software? And if you're able to mitigate issues, are these kind of issues happen all of a sudden, or are more structural and we would know about it for a long time?
So basically, the algorithm runs on this little chip I showed you. So it doesn't require so much power. I mean, I think it's an ARM 7 that is on this chip.
Okay.
And this chip, most of the computation power is for GNSS positioning and so on. So we do not have so much more power to add many algorithms. So this algorithm is not using so much resources. But what it's doing, it's basically trying to establish which satellites are in direct line of sight. And then you then compare all the other satellites against these references. So it could be several that are judged as being in line of sight. And so those will be used to judge any others against and then discriminate based on that.
Okay, thank you.
So it can act on the fly, basically. It doesn't need a long time. Okay, at start, it needs some second or minutes or two to, you know, to judge which one are really in line of sight and so on. There is a warm-up process at start, but once this is started, then it's basically automated. And so it is not done in a way that it will decide, okay, from this location, I'm always getting like large delay. So I'm just like gonna block any satellites coming from this direction, something like that. It's really dynamic. So meaning so for example, if your multipass is caused by a reflecting object, if that object change location throughout the day or throughout the week or whatever, the receiver will just adapt for that automatically. So once we have spent a lot of time and fine-tune this algorithm, you can see here on this graph that so in gray is the first generation of this receiver, and in blue, the GT88 is the improved version with this new DSS algorithm. And you can see that now at the same position, the same antenna, everything being the same, the stability the accuracy went from like on average -170 or so to probably -20. -15, so way below the 40 nanosecond required by PRTC-B. So with this DSS algorithm, our receivers are able to provide accurate time in challenging environment. That is like urban canyon, side of building, courtyards, such kind of environment. But for it to work well, it needs to have still some kind of view of the sky so that it can receive at all time one satellite with no delay, or with basically one satellite in line of sight, which in most cases it is so. I mean, when you place your antenna, usually you still have some kind of view of the sky that is clear, and the receiver is using 3 constellations. This receiver is using GPS, GLONASS, and Galileo. It's pretty much sure that at any given time it will see one satellite. Okay, in most places around the world, maybe around the poles, it's a different story, but there is no multipass, so it's okay. Yeah, so that's basically what our receivers are able to achieve in terms of multipass mitigation. And this is backed not only from this test we've done in Japan and with our partner NTT, but it is based also on many return from customer. I mean, I have many customers who have evaluated the product and came back and said, yes, it works. We have tested it like on the side window. We have tested it on location where there is multipass, and it works. So it allows basically to place your antenna in many more locations while still meeting like accuracy and stability requirement.
One question.
Yes.
Can we, let's say, increase the reliability or let's say capability of this system if we have, let's say, multiple of these receivers, and let's say one of them, let's say, running on L1, L2, L5, like a combination of these three or permutations?
Yeah, actually, that was going to be my next slide. That's a very good question. So we're going to move to the roadmap. So here, I was just showing the roadmap of our current product. So the 87 was the previous generation, and then the 88 here is the new generation, I mean, our current generation with this DSS, this advanced multipass mitigation. And then this year, later this year, like in Q4, we will release a new receiver. And this is based on a new chip that we are gonna now release to the market. And this new chip will receive also the Beidou satellites, the one that are at 1561 and the one that are at 1575. So L1, but the two Beidou constellation at L1. And this receiver will include all the same technology but improved. So like the anti-jamming will have better detection of the jammers, and also include some kind of a spectrum analyzer, so that not only the receiver detect and cancel the frequency, he also output all this information, allowing the customer to recreate basically the output of a spectrum analyzer and basically see the environment, and you would be able to see what the receiver saw before and after the anti-jam. So it allows you also to either clean up your design if there is any other source of noise, or maybe select a better antenna location and so on. It will also support the OS and NMA signal from Galileo and from QZSS. So that's authentication message. So that's also helping against spoofing, because these basically are authenticated message that you can be sure that when you're decoding them, those are not spoofed. But the receiver will not support it like this year when we launch it, because this is still not active on the Galileo and the QZSS constellation. It's still under test, but we will support it. And then we will have a secure boot, secure firmware update, and secure interface. And then next year in 2022, we will basically release an improved version of that receiver with support for L5. So it will be a dual band receiver, L1, L5, and at L5 it will receive the exact same constellation as the GT90 at L1, and at L5 it will support also GPS, Beidou, Galileo, and Navig. Navig being the Indian system.
Oh. So
India is doing a regional system like the QZSS for Japan, basically. Mm-hmm. It's covering above Greater India, and this is available at L5 and at other frequency, but not at L1, and so we will.
Any
also
reason why L2 is skipped?
Any reason for?
L2 is skipped.
So L2 is good, but L2 has different frequencies, and not all the constellation are exactly at exactly the same frequencies. So it makes the RF more complicated. And L5 being the new signal band, it has also other advantages, like the message are broadcasted faster, so it helps you with accuracy. And they are all at the same frequency, so you can make a linear receiver.
This is Charlie. Ahmad, There's also L2 is typically used by the military organizations, so we tend to stay away from that.
So one more thing, like I was wondering here. Let's say, like all fair enough, like all this interesting topics, like I mean how we look basically, like at the noise distribution, all these things. Based on that, we determine, let's say, like the authenticity of the signal that we're receiving. In general, let's say if I want to, like let's say, go for spoofing of let's say a data center or something. I see like the only thing I can push toward, let's say, in terms of vulnerability is if I create a signal where I can have imitate basically the outcome of the PPS signal in one of these receivers and be, let's say, within the margins of error that they will be accepted. Because I mean, if I, let's say, go off by 10 microseconds, let's say, the system might be able to recognize that, because I mean, in the end of the day, your system has to rely on a vote, right? It's like, should I rely on the atomic clock I have, or let's say the source of truth, or like, let's say that one is off. Do I need to like synchronize the internal clock I have with the GPS? So I mean, there's always this challenge that we need to go between. That's why, like, I often think about, let's say, a mediator. Okay, a third one comes in, like another GPS with another band, and then with this, what you're mentioning, like basically looking at the noise characteristics of the signal, you perhaps can have a better authenticity for the signal. Is that the takeaway from your method, if I want to describe in a nutshell?
Yes. Yes, because we look at the timing of the different signals, and it's unlikely that, let's say you're receiving GPS and then, so from Live Sky, and then a spoofing GPS signal comes. It's very unlikely that this signal will have the exact same timing as the one you were currently receiving, and they will also compare well to the one you were receiving from other constellations. So that's why
how if it's like the attacker basically has this complex, like, you know, complicated system in place. Let's say there's an RV somewhere, hypothetically, right, close to a data center. Mm-hmm. They have their atomic clock, let's say, on board, and they try to sync first with the GPS. They will be super aligned there. Mm-hmm. Then they will, like, I don't know, hit you with something that you also consider authentic, and then they start to sway you in a way that is with the maximum, let's say, acceptable within your, like, drifts for like the margins for the drift, and they take you off slowly and then basically throw you off, like, and I mean that's the only, like, vulnerability I can see, which I mean it's pretty severe if we get that.
Yeah, no, you're right, but first, I am not 100% sure it is so easy to create such kind of spoofing signal where they would be so synchronized to let's say GPS or any other constellation, and yet have the time to not only take a signal and rebroadcast it. They have to create basically a GNSS signal that looks like GNSS, so include all the data and everything. So it's likely that there will be a delay. Not that big, but the receiver
pass from the transmitter, the spoof transmitter, to the thing, like, I mean, you can measure that still, like.
Yeah, but I think the timing of the spoofing signal will be so let's say you're receiving Galileo and GPS, and now the GPS is being spoofed. I think even if it's well synchronized, there will be a small delay compared to what it was before with the Galileo signals, and you're also able to detect that. And
yeah,
and there is a lot of things we can do in the chip, but in the end, there is also things that can be done with antenna, and these are things we are also looking at right now. But even okay, so let's say we are in the configuration you just described, where you have an actor that is trying to spoof and is recreating some very good signal, well synchronized. As long as the receiver is able to detect that there is a spoofing, even if he's not able to mitigate for it, as long as it throws flags and say, hey, I'm being spoofed, then you have the chance to say, okay, I don't rely on that one.
Yeah, go atomic clock. Yeah.
So that's our primary goal, to be able to detect.
Because you don't have feedback. You don't have the feedback of like how the receiver is reacting. You may do whatever you want. The receiver will ignore it. You don't have you don't have that information when you trip through, like, let's say, one of these safety margins or something. Yeah, I agree with you. That's a good point. But still, it's keep me awake in the night. Like there's huge vulnerability here.
Yeah, it's important that there is that the receiver is being able to warn that spoofing is happening. And truth be told, I think it's better that it's a bit too sensitive and warn a bit too often than not.
Yeah. That's why you have atomic clocks. Yeah,
that's why. And then most likely you have several points on the network where you have GNSS receivers too, so you're probably able to use that as an information. Yeah. If you have any other question,
there were no questions in the chat so far, so let's see if the team on call has any.
Maybe one more question, like the form factor for your products. Are these do you guys support this? I don't know what it's called. Like I know the U-Blocks has the RCB form factor. You guys have that one?
Currently not, but our receivers, I mean, the GT87 or GD88 is, so basically the form factor you're talking about from U-Blocks is it's just a timing receiver, just like our GT88. So we could, in being smaller, we could easily make a carrier board and mount it on it. We haven't done it, but this is fairly simple to do.
No, you've seen the one that's on the time card, right? So that is something. I hope that thing becomes more like a standard, because I know Trimble has also another like product that fits exactly the same pinout, like the 2x4, the 8 pins. So that would be
actually, originally there was a timing module from Motorola that was a bit smaller than this module you're talking about. This was the standard at the time, like 10, 15 years ago. And then it went away, and we had one that was compatible. And these days the demand is very small for this kind of module. But this one we could make it. We don't have it today, but it's fairly easy to make a carrier board and mount our GD88 on it, which is a SMD type. So
we might be able to. Speaking on behalf of, let's say, OCP, like the whole like this the timing card project, we might be able to maintain, let's say, PCBs who cooperate, let's say, with you guys, with U-Blocks, with Trimble, with like everyone that is interested in this, and we have the boards that, like, we can have them in a repository that everyone can utilize, like, to put their modules on if anyone chooses to. So that could be a
good solution. Ahmad, actually, El Proma, I think, made a presentation once. They make these boards, and they make one with our GT88 actually.
Awesome.
So we don't make one Furuno, but we have a customer that makes one with our product. So, and we will support it. So if you wanted to test, you could get one from El Proma, and I will support you. Basically.
Wonderful.
Thank you very much, Furuno team. I think this has been very good information, practical for us who are looking to deploy GNSS receivers in our data centers. I do encourage everyone to approach Furuno for any questions. The slides and the video will be posted online on our wiki page. And you can see there also the plans for the next call, 2 weeks time.
Awesome.
Thank you very much. Thank you for hosting us.
Merci beaucoup,
Thank you, guys.
Benoit.
Thanks
Merci,
very much,
Shirley.
guys.
Okay.
Bye, everyone.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.